Today we completed the part 2, that is linear programming, right? And also we looked into the graphical method. So I'll just go through this slide and then I'll continue with the next methodology which we are able to continue today. So see, just to conclude our graphical method technique, okay, it works directly for exactly two decision variables, right? That is what is noted here. And the central theorem is that if an linear programming has an optimum, at least one optimal solution occurs at corner point of a feasible region. And the next is the practical procedure is plot constraints that identify the feasible region. So find every feasible corner there, evaluate the objective at each corners and choose the best one out of them. Someone wants to join. Yeah. So the next thing is you can see there we also need to recognize the multiple optimal solutions, unbounded problems and infeasible problems also, right? So now considering the limitations, a realistic power system optimization may have hundred of just give me a second. Yeah. So so the limitation is a realistic in any realistic power system. They may have hundreds, thousands, or even far more distant variables. So we cannot draw 1,000-dimensional feasible regions. It's not at all possible. So we need an algorithm method that preserves the corner point idea, but it also removes the two variable restriction what we have in our graphical method. So what I'm going to suggest you is to overcome this of the graphical method, we can have the next method that is called simplex method. How come everyone joining to the class today? Anyways, so this is the third part of our second session, that is the simplex method. So now we have few questions here. Why we need the simplex method? I think most of this part is answered in the previous two parts, right? So if you remember, before we began the calculation is this, simplex moves from one corner point of the feasible region to another, improving the objective until no further improvement is possible, the first thing. The second is, in graphical method, we could see the corners. In simplex method, we do not draw them. Instead, the tabula contains the algebraic information needed to move between basic feasible solutions. So we will use the same production example that we had already solved in our first method, also in the second method in graphically, right? This is a deliberate, fine. I want you to see that the simplex procedure and the same answer as the graphical method. So the same answer as the graphical method, and the two methods are not solving different problems there. So there are two ways of navigating the same feasible set. Okay. Well, and see the graphical method has a dimensional limitation. Okay. If you have two variables, we can draw two axes. With three variables, visualization becomes difficult. With thousands of variables, it is highly impossible. Okay. So considering the realistic power system, uh, that linear programming, we may have variables for multiple generators, multiple time periods, transmission constraints, reserve quantities, piecewise linear cost segments. I'm just giving you a few names. Okay. So the resulting linear program can easily contain thousands of variables. So simplex was developed to solve such LPs algebraically. The method was developed by George Dantig in 1947. The method was, with this classical simplex algorithm, it is dating back to 1947. Okay, it was developed in 1940, and then the simplex algorithm was dating to 1947. The basic idea is, surprisingly, it's initiative, right? See, imagine that every feasible corner point is a location in a landscape, and objective function tells us how high or how low the location is. So simplex starts from feasible corner, and moves to a neighboring corner, that improves the objective. It continues doing this until no neighbor move can improve the objective. So it will reach to a point where you have complete final uh, solution there. Okay, there is no possible solution beyond that. So modern LP solvers also use method other than classical simplex, especially interior point methods. But learning simplex is still valuable because it gives us a clear understanding of basic changes, reduced costs, constraints, and dual informations also. So the essential idea is therefore not the tabula itself. The tabula is the bookkeeping mechanism that tells us which corner we are at end and how to move to the better one. Fine. So one additional point here is simplex is not the only way to solve linear programming. Modern optimization softwares also uses interior point. Uh, just a, yeah. So interior points and other methods. So the purpose of learning the classical simplex procedure is to understand the structure of LP solution, not to imply that every modern solver literally performs only the hand calculation. Yes, this is the tabula we are talking about. See, this is the setting up of initial simplex tabula here. So let us consider the initial simplex tabula for our production problem. Okay, so the linear programming, give me a second, please give me a second, I'll be back. Hello sir. Hello. Sir, ಹೇಳಿ sir. ಸರ್ ನಾವು Yeah, I'm sorry. These interruptions are there. Well, so I think in the first two methodologies, we have looked into that maximizing and minimizing thing. Okay, if you want, just I can run back my slides and I can show you where all it started for us. Yeah, this was a production problem. If you can see here, the maximize was Z40x1, right? Plus 30x2. I think Mamta can remember this part where what we started the other day, right? This was a question. Okay, the factory makes two product A and B. Product A earns 40 rupees profit and needs 2 hours of machining, and all these things we have discussed. We have discussed the two methodologies also, and the answers were same. Okay, right. So we will try the third method now. Okay, that is simplex method. For the same numerical, the question remains the same. Okay, moving ahead, you already know that the maximizing equation Z is equal to 40x1 plus 30x2, right? And you have a subject to. What is a subject to? Like you have a constraint. The constraint is that 2x1 plus x2 plus s1 is equal to 100, and x1 plus 2x2 plus s2 is equal to 80. So you know this all these scenarios from the previous parts. So with all variables, you can see they are all non-negative here, so no problem with the negative part. So the initially tabula is arranged with the basic columns x1, x2, s1, s2. You have x1, x2, s1, s2, right? And these are multipliers for you, and these are constraints for you, right? And moving ahead, on the right hand side, the first row corresponds to s1, that is 2 1, right? 2 1 1 0, and the second second row gives you the S2, that is 1201, right, and 80. So this is what we have data, and this is how we have the initial tabula. So the objective row is written in classical maximization convention as you can see here: -40, -30, 0, 0, 0. Why are the objective coefficients negative here? Any answer? Answer is on the slide. Are you people here? Excuse me. Uh, I mean, others, Rashmi, Sanjita, sorry, Shivraj, Sneha, Uday will be there. Others have just switched on and they have left, I guess. Shivraj? Nice. Okay. Yeah. See, why we have placed them negative is there is there is a scope for improvement in the value of the Z. So, how much you improve? Like if you improve 5 points, it become -35 here. Okay. If you improve by the x1 coefficient, if you improve the x2 coefficient by 10 points, this becomes -20. That is, you are getting nearer to the improvisation. Okay. So this is the idea behind that. So this tabula is called bookkeeping convention. Okay. In this form, a negative number is in the Z row tells us that increasing the corresponding non-basic variable can improve the objective. So at initially basic solutions of x1 and x2 are 0, right, and therefore s1 is 100 and s2 is 80. This is exactly the origin that we started. If you want to see in graphical method also, this was a problem. No, this was a problem. See, we started at 80 and 100, right? Well, so this is exactly the origin. Now look at the Z row here, this row. We have -40 under x1 and -30 under x2. Both are negative. So we are not optimal yet. We need to choose the one variable to enter the basis. So the word basis is central to simplex. With two equality constraints, we need two basic variables. Initially, those are S1 and S2. As algorithm progresses, X1 and then X2 enter the basis. Okay. So the basis therefore records which variable define the current corner point. So here it is much more clear for you because we have a flowchart kind of explanation. So the simplex algorithm can now be stated as a sequence of steps here. First, check the objective row. Objective row will always be this row. I'll choose for the pen so that we can write and yeah. So this is the objective row for you. Okay. Well, so moving ahead. This is over here. So check for the objective row for optimality. Okay. In our maximization convention, if no negative entry remains in the Z row, the current solution is optimal. That is, here if this becomes positive, even it is 0 also it's positive. So if these two, the entire row becomes positive, then optimality as reached. There is no further optimality can be achieved. But at this point, we have -40 and -30, right? So there is scope for optimization. Moving ahead, if negative entry remains there, choose the most negative one. The corresponding variable becomes the entering variable then. So next, performing the minimum ratio test here, divide each positive entry in the pivot column into the corresponding right hand side. Okay, ignore rows where the pivot column entry is 0 or negative. So the smallest non-negative ratio identifies the leaving variable there. Fine. And the instruction of entering column and leaving row is the pivot element. Okay. Then we perform row operation so that the pivot becomes 1 and every other entry in that pivot column becomes 0. So this produces a new tabula and therefore a new basic feasible solution. So we repeat the process. Okay, and why do we use the minimum ratio? Because we want to move as far as possible in the direction of entering the variable without violating the uh, feasibility. If we move further than the smallest permissible ratio, at least one basic variable would become negative there. So the ratio test is not an arbitrary calculation. It is the algebraic equivalent of staying inside the feasible region, okay, while moving towards a better corner. When you perform the ratio test, never divide by negative or 0, okay. uh, so pivot column entry is standard and primal simplex procedure. So a negative entry does not impose the upper limit or how far the entering variable can increase in that direction. So a positive entry is what can eventually force a basic variable to reach 0. Okay. So sorry. Yeah. So if you have gone through this flow chart, the ratio test is also being explained. Okay, the step by step procedure is also explained. So now we can have an worked example here. So iteration 1, we are trying to have the iteration 1 choosing the pivot here. So let us perform the first simplex iteration. Our initial objective row contains minus 40 under x1 and minus 30 under x2. So we select the most negative, which is minus 40. Therefore x1 enters the basis here. Okay, now we perform the ratio test using x1 column. So this is your x1 column. Okay, for the first constraint, the right hand side is 100, agree, and x1 coefficient is 2. How you got to know the x1 coefficient is 2? From the constraints. If you go back and if you look into the equation here, you have the constraints, right? 2x1. So you have the coefficient of x1 as 2 here. Well, for the first equation, or else here also you got coefficient of x1 is 2. Okay. Therefore, the ratio is 100 divided by 2. Here you have the ratio test. Okay, 100 divided by 2, that is you get 50. Similarly, we come to the second row. You have 80 and you have coefficient as 1, then you get 80 here, right? So the pivot row for minimum non-negative 0 is 50 and 80 got by these things from the S1 row. Okay, are you understanding the procedure here? So the second constraint, I mean, we have dealt with the 80 here, right? So the pivot element is the intersection of x1 column and the s1 row. It is 2 there. So let us interpret this geometrically. We started at the origin. We are trying to increase x1 because it improves the profit most strongly. So the first resource constraint becomes fully used after x1 reaches 50 and x2 remains at 0. Therefore, we cannot move any further in that direction while remaining feasible. This is why S1 leaves the basis here. So the arithmetic of the ratio test is telling us exactly what the graph told us. That is, we are moving from the origin towards the corner at 50, 0. Yeah, here. Can you see here? 50 and 0 here, right? This was the first one, if you remember. And the entering variable is chosen from the objective row because it identifies the variable with the greatest immediate opportunity to improve the objective under this convention. The leaving variable is chosen from feasibility consideration. Therefore, one decision is economic and the other is physical. So, which variable promises improvements and which constraint stops that improvement? Okay. So here again, I'm still moving with the iteration 1 only. We are done with this. We will move on with the next iteration now. So now we perform the pivot operation. So the pivot element is 2. Our first task is to make the pivot equal to 1. Therefore, we divide the entire first row by 2. If you divide the entire first row by 2, this becomes 1, this becomes 0.5, 0.5, and this becomes 50. Same thing, right? Well, so now, since x1 is now the basic variable in this row, the other rows must have 0 in the x1 column. So we are making them as 0 here. As you can see, you had 1 and minus 40, but we are making them as 0 in this point, right? So for the second row, we subtract the new first row from the original second row. Okay, so you had a original second row here, and at the second iteration we have divided this by 2, so we have 1 here, right? We have made this as 0, we have made this as 0 already. You got 0.5 here because we are dividing it by 2, and here also it is 0.5. Right, and this is obviously 0. Fine, same thing you have here. See what I have written in the red pen: 1.5, 0.5 and 0. You have 1.5 and 0.5 and 0. What we have done, we have divided the entire thing by 2. And now what are we going to do to set up the second row? Understand, we are dividing, we are subtracting the entire thing. Okay, this thing minus of this red portion what I have written. What is 0 minus 1? Hello. Yeah, now we are subtracting our second row. Okay, with the first row from the original second row elements. Okay, so original second row elements, you had 1, right? 1 minus 1 is 0. Anyways, this was 0 from initially, don't worry. Here you have 2 minus 0.5, 2 minus 1, you get 1.5. Then you have what we have, 0 minus 1.5, you will get minus 0.5, and then you have 1 minus 0, you will get 1. But look into the RHS here: 80 minus 50, 80 minus 50 is 30. You got 30 here, right? So this is how we have created the second row now. Okay, now we eliminate x1 from the objective row. Okay, because we have to carry out here also, I guess. Minus 30, yes. No, previously. Wait, I'll explain it. We are done with the second row now. We will move on with the next part. So we are talking about the objective row. Now we will eliminate x1 from the objective row because objective row contains minus 40. Okay. What we will do, we will add. We want to eliminate this. So what I will do, I'll add 40 to this. What happens if I add 40 to this? What you will get? 0. Yes, you got 0 here. If I add 40 to this, what you get? 10. Yes. Similarly, yeah, when you do this, here we had, yes, minus 40 minus 30, right? So the new parameter what you are going to get is 0. Here you will get 0, and this you get 10, positive 10 actually, and here we get here it is, yeah, you get 20. Okay, and you get 0 here. So here, because your first row was 0, okay, and this we multiply with this, you will get 2000 here. Okay, So our new tabula is ready now with X row having 1.5, zero point 0.5 and 0, 50. X2 is 0, 1.5, minus zero point 0.5, 1, 30 and 0, minus 10, 20, 0 and RHS is 2000. So now we stop and interpret the results. Our current basic solution is x1 is 50, x2 is 0 and s2 is 30. The objective is 2000. I'm just talking about this column now, right? This matches our graphical corner 50 comma 0 if you go back and if you have a look, but we are not optimal because z row is still z row still contains one negative number, that is minus 10. Okay, so what can we do with this? That's the question. Okay, so what we should do here is uh, therefore increasing x2 can still improve profit. So what can we do? This is exactly what we saw graphically. The corner at 50.0 was good, but corner at 40.20 was even better, right? I think we discussed this here, here. Yeah, this was good, but this was even better region for us in terms of profit, right? So this is the same thing as been illustrated even with the simplex method also. Okay. Now, how to write the how the right hand, excuse me, till my waist ಆಗುತ್ತೆ ನೋಡಿ ಅಷ್ಟೊಂದು ಇದೆ ಇರ್ಬೋದು. Yeah, 1 meter. Yeah, yeah. Yeah, I'm sorry, we have some international delegates coming over, so we are in the verge of that preparation. Anyways, well, I was talking about the interpretation of how we solve this, how we obtain to this tabula here. So, see, you can notice there, the right hand side of the Z now become 2000. This is not the accidental. We have reached the corner point represented by x1 equal to 50 and x2 is equal to 0. So, the actual profit is 40 multiplied by 50, right, which is 2000. Okay. Uh, this tabula is therefore carrying the same physical information as our graph, what was initially our graph was looking into here, the 2000, this tabula. This is what I was trying to explain you. Okay, so when it comes to iteration 2, the final pivot here, because there we had a minus in x2 in the last component, we want to improve it, right? So we perform the second iteration. The only negative entry remaining here is in the z row, that is minus 10, that is under x2. You can see here, this is the only thing what we are supposed to change. Okay, so now what happens is now perform the ratio test using x2 column. Okay, so for the x1 row, the ratio is here, the ratio is I'm talking about x1 column, yeah. So 50 divided by 0.5, which is equal to 100. Okay, and for S2 row, the ratio is 30 divided by 1.5. Initially you had 30 divided by 1.5. Here 50 divided by 0.5. Okay, so 30 divided by 1.5 will give you. Sorry. Madam.
Sir, sorry, I'm calling you again and again.
Yeah. What happened?
ಇದು ಹೂವ ಎಷ್ಟು ಬಡ್ಜೆಟ್ ಅಂತ ಇರ್ಬೋದು?
Go up to 1000 rupees, it's fine. Yeah. So I was talking about the ratio now, right? So you have 30 divided by 1.5 okay, that will give you 20. So the minimum positive ratio is 20, therefore S2 leaves the basis now. So the pivot element is 1.5, okay. We divide the pivot row by 1.5 and then use the row operations to eliminate x2, okay. So x2 from other rows, so the resulting tabula is approximately what you will get is 1 0. What we are going to do is we are dividing it by 1.5, right? So what you are going to get is 1 0.67 minus 0.33 and 40. Similarly here also 0 1 0.33 0.67 and 20. Here it is 0 0 16.67 6.67 and 2200. As you can see, you don't have any negative element in the objective row. And also look at the profit, and look at the profit here 2000, but here it is 2200, right? So the basic variables are x1 is equal to 40, x2 is equal to 20, the objective is value is 2200. Compare this with our graphical solution here, okay, we obtained exactly the same optimum value there also. This is very important moment. You know, the graphical method and simplex method are not unrelated procedures. The graphical method showed us that optimum is at corner 40 comma 20. 20 comma sorry, so simplex reached that same corner algebraically by changing the basis twice. So the new right hand side of the z row is 2200, which is actually a profit at x1 is at equal to 40 and x2 equal to 20. So the two pivots have therefore moved us from yeah, they have moved us from origin to the first useful corner and then to the optimum corner, okay. This is algebraic version of the graphical journey. well well so uh, reading the optimal tabula, let us learn how to read the final tabula now. See, the first rule is simple. Basic variables are taken, basic variables takes the values as shown in the right hand side of the column. Therefore, our basic variables, our basis contains x1 and x2. Therefore, 40, x1 is equal to 40 and x2 is equal to 20 from here. From here it is 40 and from here it is 20. Fine. What about variables that are not in the basis? They are non-basic and in the current basic solution and they are 0. Okay. Therefore, S1 is 0. You can see here S1 and S2. You need to, they are not 0 on the tabula, but as variables are, they are not in the basis. Okay, so the non-basic and in the current basic solution, we will consider them to be 0. And the physical interpretation is important. Okay, S1 0 means there is no unused machinery capacity. The machine times constraint is binding. Similarly, S2 is equal to 0 means all the available labor capacity is being used. So the labor constraint is also binding. So the objective value is read from the right hand side, right, of the Z row, that reads as 2200. So you have got a new Z value here. So now we encounter another important concept that is called shadow price. You can see here at the last. The entries associated with the slack variables in the final objective row, as you can see here, S1 and S2, they are not 0. You have some value there, right? So, uh, that provides the information about marginal values of relaxing the corresponding resource constraint under the tabula, convention being used. Okay. In this example, the values are how much is the value? 16.67 and 6.667. So we can interpret such values as the marginal improvement in the objective associated with one additional unit of the corresponding resource. within the range over which the current basis remains valid. Later, when we discuss power systems, this idea becomes closely connected to marginal cost, lambda, and location pricing. Okay, so shadow price should be interpreted locally. If the available resources changes by a small amount while the current optimal basis remains unchanged, the shadow price indicates the corresponding marginal change in the object. Okay, so it is not uh, necessarily valid for a large change in the resource, because a different constraint may become binding there. There are special cases, but now they are visible algebraically. So the simplex tabula also let us recognize special cases algebraically. The first is the unbounded problem. Suppose a negative z row is z row entry tells us that a variable wants to enter, right? But every coefficient in that pivot column is 0 or non-negative. Then there is no valid positive ratio. So there is no leaving variable to stop the movement. Algebraically, the problem is unbounded in that direction there. Okay. So the second is degeneracy. This occurs when basic variables has right hand side equal to 0. The algorithm there also can sometimes move from one basis to another without improving the objective, or can even cycle in specially constructed cases, like rules such as we have something called Bland's rule can be used to prevent cycling there. The third is multiple optimal solutions at an optimal tabula. If a non-basic variable has zero coefficient in the objective row, it may be possible to bring that variable into the basis without changing the objective value there. That signals an alternative optimum also. Okay, so these three cases corresponds directly to what we saw graphically. The graphical method made them visually obvious. Simplex makes them visibly through the algebraic condition. This is one reason it is useful to learn both methods, like the graphic method and the simplex method, because graphic methods will build intuition for you and the simplex tabula provides an scalable algebraic procedure. See, degeneracy is worth remembering because it reminds us that basis and physical points are not always uniquely related. Different bases can sometimes describe some geometric points. This is one reason optimization theory distinguishes between a solution point, a basic solution, and an optimal basis. So the challenge is handling is equal to and greater than or equal to constraints, the artificial variable. See, we now need to address an important issue here. Our first example was convenient because all constraints were less than or equal to constraints there. None of them went beyond the constraint. There were no unrealistic demands. Uh, that gave us a slack variable and an obvious starting basic feasible solution. In real power system, what happens is problems are not always that convenient. The power balanced equation is an equality. Sum of generations equally demand equal. I mean, sum of the generation equals demand. Minimum generation or minimum output requirement may appear as greater than or equal to constraints. For greater than or equal to constraint, a surplus variable can convert the inequality into an equality, but resulting surplus variable has negative coefficients in the constraints and does not automatically provides a convenient starting basis. So the standard solution is to introduce an artificial variable. It is artificial, why? Because it does not represent a real engineering decision there. It is temporarily introduced to help us start the algorithm. So there are two classic approaches for this. Okay, so the first one is called Big M method, and artificial variables are assigned. A very large penalty in the objective. So the simplex process is therefore encouraged to drive them to zero. The second is the two-phase method. In phase one, we solve an auxiliary problem whose purpose is to eliminate an artificial variable. And once a feasible solution to the original constraint has been obtained, phase two solves the actual engineering objective. So, uh, there is another very important idea in linear programming that is called duality. If you remember in the very initial classes, it's on Monday when I was introducing you to the linear programming techniques. I had discussed about this. I think on Tuesday initially. Yeah. So every linear program has an associated dual problem. It is useful to think of the primal and duals as two different questions about the same system. Suppose the primal problem asks how should I use limited resource to maximize profit. The dual problem asks what is the economic value of those resources. See, if a factory has a limited amount of machine time, the primal decides how to allocate that machine time. The dual tells us how valuable an additional hour of machine time would be optimum. In the power systems, this idea uh, it becomes even more meaningful. You know, a power balance constraint has marginal value associated with it. So in economic dispatch, we often introduce the terminology called lambda there. So our system's marginal cost has the incremental cost of serving an additional unit of demand under the current operational conditions. Well, so LP duality provides a rigorous mathematical foundation for the for that marginal values interpretations, right? So in network constrained power markets, dual variables associated with network constraints uh, contribute to locational price formations. So the exact market formulation can be more sophisticated than the small LPs, okay, where small LPs we are studying today, but underlying I'm sorry, yeah. So, but underlying idea is same. Optimizing does not only give us the dispatch variables there, it can also tell us the marginal values of constraints and resources. So, duality is not an optional theoretical chapter here. ಹೇಳಿ ಸರ್.
ಹಲೋ,
ಹಾಂ ಹೇಳಿ ಸರ್.
ನಾಯ್ಡದು ಸ್ಟ್ಯಾಂಡಿಂಗ್ ಮಾಡಿಸ್ಬೇಕಂತ ಈಗ ಕೇಳ್ಸವ್ರೆ.
ಯಾರು ಹೇಳಿದ್ರು ಸರ್?
ಪ್ರಿನ್ಸಿಪಲ್ ಸರ್.
ಸರ್ ಪಾಸಿಬಲ್ ಇದೆನಾ?
ಅಲ್ಲ, ಹೊಸದಾದ್ರೆ ಮಾಡಿಸ್ಬಿಡ್ಬೋದು. ಫೋನ್ ಮಾಡಿ ಹೇಳಿದ್ರೆ ಕಳಿಸ್ಬಿಟ್ರೆ ಹೊಸದ್ ಮಾಡಿರ್ತಾನೆ, ರಾತ್ರಿ ಕೋಲ್ಟ್ರು ಮಾಡ್ತಾನೆ, ಬೆಳಿಗ್ಗೆ ಎತ್ಕೊಂಡು ಹೋಗ್ಬೋದು.
ಆಯ್ತು, ಹಂಗೆ ಹೊಸದೇ ಬೇಕಾಗಿರೋದು ಈಗ.
ಹೊಸದ ಅಲ್ಲ, ನಮ್ಮ ಹತ್ರ ಪೋರ್ಟ್ರ್ ಇದು ಸ್ಟ್ಯಾಂಡ್ ಇದಾವಲ್ಲ ಸರ್, ಹೊಸದಾದ್ರೆ 2801.
ಓಕೆ,
ನಾವು ಕಳ್ಸಿದ್ರೆ 1500 ರೂಪಾಯಿ
ಸರ್. ಹೊಸದೇ ನನಗೆ 1750 ಮಾಡಿಕೊಟ್ರು.
ಎಲ್ಲಿ?
ಪುತ್ತಗೇರಿ.
ಪುಟ್ಗಿರಿ ಮಾಡ್ಕೊಟ್ಟ? ಅವನ್ನ ಕೇಳ.
ಹಾಂ ಕೇಳಿ ಕೇಳಿ ಕೇಳಿ
ಹೇಳ್ತೀನಿ.
Yeah, I'm sorry. So, duality is not a theoretical chapter, you know. It contains optimization, mathematics to engineering, economics to electricity, market interpretation, everything. So, the dual viewpoint also explains why a constraint that is not limiting the optimum value has little or marginal value. Okay. If a transmission line has substantially used capacity, So if it is having an substantially unused capacity and we increase its limit slightly, so the current dispatch may not change at all. Therefore, marginal value of relaxing that constraint can be zero also. Okay. So how do we solve LP problems in practice? See, at this point, an obvious question is, do engineers really solve large LPs by drawing tabula on paper? See, certainly not. If that is your question, no, we are not going to solve it by using paper and pen. So, what is the approach engineers do practice? A realistic power system LP may contain thousands or millions of variables and constraints. Software is used to solve such problems. Classical simplex is one of the family of algorithms, which while modern solvers also use interior points and other advanced methods. See, you can use MATLAB. In MATLAB, a common function of linear programming is linpro. It is useful for either for teaching or else for research prototypes and engineering optimization studies. In Python, you have SciPy, which provides linear programming, and packages such as we call it as pulp at POLP can be used to construct LP models. From small technical example, Excel solver can also be useful because it makes the decision variable and constraints visible. For large industrial optimization, commercial solvers such as Simplex and you have Gurobi are widely used, and GIMS provides an modeling environment that can connect mathematical formulation and optimization solver. The important lesson is that learning Simplex is not about becoming an human calculator here. Okay, so what we need to do here is it is about understanding the logic behind the solver. When software reports an optimum, an engineer should know what the variable mean, which constraints are binding, what are the I mean what the objectives represent, whether the result is physically reasonable. So, software should automate the computations, not replace engineering judgment there. In practical work, the modeling layer is often more important than the solver layer. Therefore, a function such as linpro can solve the equation we give it, but it cannot determine whether we forgot a generator limit, use the wrong sign for a power balance equation, or mix the megawatt and kilowatt. Those are modeling responsibilities. Okay. So now the entire part 3 we can put it into one slide. So let us summarize the simplex section before we move into the power system applications here. So the central idea is that simplex moves from one corner of the feasible region to the another, improving the objective until no further improvement is possible. For our maximum tabular convention, the most negative entry is Z-row, identifies the entering variable, right? The minimum positive ratio of right hand side to pivot column coefficient identifies the leaving variables. The pivot operation changes the basis and produces a new basic feasible solution. We stop when no negative entries remains in Z row. That is what we want, right? And when equality are generated, then are equal to constraints prevent us from constructing a natural initial basis. Artificial variables may be introduced using big M or two-phase methods, right? So these are the most important things. But finally we spoke about duality also. Duality gives us a shadow price information in power system language. This connects to the marginal cost or lambda concept introduced earlier. We now have all the basic LP machineries. The remaining question is the most important one for this topic of discussion. That is, how does the machineries apply to actual power system? uh, when you know when real generator costs are not linear. At this point you should be able to describe simplex without using the word tabula. Start from feasible corner, identify the direction that improves the objective, move as far as feasibility allows, arrive at a new corner and repeat. So the tabula is simply the efficient algebraic mechanism for doing this in many dimensions. The next part, the last part of this, actually it was supposed to be completed in the second session itself. Due to the technical glitch, due to the many other things, we ended up the other day, right? My laptop ran out of battery. Well, so now applications in power system. So how are we going to apply all these three techniques what we studied in the power system? Of course we have dealt with the one simple problem and we try to understand there. See, everything we have studied so far has been general optimization theory, right? Now we can bring it back to the engineering problem, and that motivated this entire session. See, economic dispatch normally uses a quadratic generation cost curve. Transmission network have nonlinear AC power flows relationships. Generator operating decisions may also involve discrete on and off state. So why use LP? The answer is that linear approximation can provide extremely fast optimization while retaining a structure that can be solved reliably reliably at a large scale. So we will first understand the most important approximation, that is piecewise linearization of generator cost. Then we will formulate a complete linearized economic dispatch problem. So finally we will add network constraints and arrive at the OPF concept. See, this is where abstract ideas of variables, constraints, simplex, and duality becomes practical tools for power system operation. Why linear programming gives real costs or quadratics? See, let us confront the apparent contradiction directly here. What's that? In session 1, we said that generator fuel cost function is naturally represented by the equation. I have given the equation here also. There also we discussed the equation. I think it is there in your PPTs I have provided in the first class. See, okay. So this is a quadratic function, right? Strictly speaking, economic dispatch with this objective is a non-linear optimization problem. So why have we spent today's session during studying LP? Because an engineering optimization model does not always have to represent every physical relationship exactly, right? Sometimes the practical requirement is to obtain high quality decision quickly and reliably. Suppose the true cost curve is smooth and curved, we can approximate it by a sequence of straight line segments. Each segment has a constant slope. Once we use those segments as decision variables, the objective becomes linear. So the trade-off is straightforward. A non-linear model can represent the original curve more accurately, but may, I mean, they may require more computational effort there. So a linearized model introduces approximate error, but can be solved using high efficient LP machineries. This becomes especially attractive in large scale operational problems, okay, where optimization is repeated frequently. So the important point is not that LP is better than nonlinear programming in every situation. It is that LP is a useful engineering approximation when speed, scalability, predictable computations are important. So piecewise linearization is therefore the bridge between the quadratic cost curve from session 1 and the LP formulation we are learning today. Well, see, this is an important engineering judgment here. We do not linearize because the nonlinear curve has become a linear in reality. We linearize because a simplified mathematical representation may be sufficiently accurate uh, for decisions we need to make. So model accuracy and computational cost must therefore be considered together. Okay. Well, precision linearization of the cost curve. This is very much important. See, uh, if you can imagine two generator cost curves as a smooth upward curving function of generator output, instead of representing that curve with one quadratic equation, we divide operating range into several sections. Within each section, we replace the curve by a straight line. The slope of a segment represent the average incremental cost over the interval. If one segment covers 0 to 100 megawatt and another covers 100 to 150 megawatt, the second segment may have higher slope because the generator becomes more expensive to operate as output increases. Well, so the quality of the approximation depends on how many segments we use and where we place the breakpoints. With more segments, the straight line approximation follows the original curve more closely, but every segment introduces an additional variable into the LP. Okay. So optimization problems becomes larger there. See, with few segments, the model is smaller and faster, but approximation error increases. The important conceptual point is that each segment has constant marginal cost. This allows us to treat the problem as a linear merit order problem. Use the cheapest available segment first, the next cheapest, and so on. This subject to all system constraints. So the graph on this, I mean, we can move on to the complete linearized economic dispatch. See, now let us formulate the complete linearized economic dispatch problem. Suppose generator I is divided into k cost segments, which introduces a decision variable for the amount of generation assigned to segment k of generator I. Each segment has constant slope m, right, ik. The that slope represents the cost per megawatt hour associated with that segment. The objective becomes minimize z is equal to sum over I, right. I was just trying. Did I try to putting all these equations into the PPT is, it's very tedious task because many a times we don't find those symbols of summation and all. Anyways, so MIK is multiplied by PGI So this is linear. Okay, now we need the power balance constraint, sum over I and k of pgi k minus pd equals 0. Okay, this says the total, here we have subject to equation is here, minimization equation is here. Okay, so now see, the total generation assigned across all generators and all segments must exactly meet demand. Under the simplified lossless formulation being used, okay, here every segment also has a maximum width. Therefore, 0, this equation, segment width 0 less than PGI or K less than WI K. So the total output of the generator I simply the sum of its segment outputs. Okay, so that is given by PGI is equal to, I mean, yeah, PGI is equal to sum over K, sum, here it is, total output. Okay, summation of K and PGIK, this is the final output. Here you have the minimization equation, here we have subject to constraints, right? So see what has happened, the original quadratic cost has disappeared from linear programming formulation here. It has been replaced by several linear segments variables and their associated constant cost rates. At this point, the problem is completely standard linear program. The same formulation principle, graphical ideas, simplex logic, and duality concepts that we studied earlier now apply directly to a power system problem. For example, if generator I has 3 segments with width 50, 70 and 60 megawatt, the 3 corresponding segment variables cannot exceed those widths. The generator's total output can therefore range from 0 to 180 megawatt. So the segment variables are not independent generators, they are portions of the same generator operating ranges. Okay. Now we can look into a complete linearized dispatch. We can have a work numerical. You can see here. So generator 1 cost are linearized into, one cost is linearized into 2 segments. 0 to 100 watt is 5 megawatt hour, 0 to 100 to 150 megawatt is 7 megawatt hour, right? Rupees 7 per megawatt hour. I'm sorry. Generator 2 is a single segment, that is 0 to 120 megawatt hour. You have 6 rupees per megawatt hour. Demand is 180 megawatt, right? Minimize total cost. Now we have to minimize the total cost. So what shall we do? uh, gen, uh, the total demand is 120. Have they given the total? Yeah, here it is 180. The total demand is 180 megawatt. Okay. The first step is to rank the available segment by cost. The cheapest is generator 1, first segment. As you can see, generator 1, okay, first segment is costing you 5 rupees per megawatt hour. The next is generator 2's 6 rupees per megawatt hour, that is of generator 2, all right. And the last one is generator 1's second segment, that is 7 rupees per megawatt hour. We therefore load the cheapest segment first, that is generator 1 first segment can supply 100 megawatt. So we use the full 100 megawatt there, okay, at the cost of 5 rupees per megawatt hour. So you will be costed 500 rupees per hour. Okay. Demand remaining is 80 megawatt because 100 megawatt has been supplied by, I'll write everything, you can have a look. Generator 1, segment 1 will supply 100 megawatt, which is costing you at rupees 5 per megawatt hour, and so total generation we have is 500, right? But what is the leftover? Total demand is 180 and we have 100 megawatt hour here already been supplied at the rate of 5. So 180 is my total demand and 100 are already supplied. So you will get, you are left out with 80 megawatt hour. Well, sorry, 80. Well, the next cheapest is generator 2 at rupees 6 per megawatt hour, right? Its capacity goes up to, you can see generator 2, it goes up to 0 to 120 at 6 rupees. So we will generate this 80 megawatt hour from generator 2 at 6 rupees per megawatt. So how much this will cost? Yeah, I'm doing for 80 rupees. So what is the total cost? Here you have 500, here you got 480, total you will be having 980. The final dispatch is dispatch. This is the total cost. The dispatch is PG1, that is the power from the generator 1. You have 100 megawatt. PG2 is 80 megawatt. Total cost is 980 per hour. Your total cost. See, generators once second more expensive segment is not used because demand has already been satisfied. This is the same economic principle we saw earlier. Use the cheapest available marginal generation first, subject to capacity constraints. Notice the numerical example can be interpreted directly as an linear program solution. The cheapest segment is filled first because its objective coefficient is smaller or smallest. The next segment is then used until demand is satisfied. If network constraints or other restrictions were added, we could no longer rely on simple merit order alone. Okay, the LP solver could determine the globally feasible allocation. Shall we have a 5 minutes of break, Mamta? Yeah. Yeah, let's continue. We'll talk about the DC optimal power flow. Okay, so economic dispatches. See, we are trying to look at the, I mean, at a network scale here, the linear programming. So, economic dispatch by itself does not know whether the generators and loads are located. I mean, where they are located. Okay. Suppose the cheapest generator is located far away and from the load, and the transmission line connecting them has limited capacity. Economic dispatch may tell us to use the cheap generator heavily, but resulting power may not be physically deliverable, right? So there is where we are moving out of economical dispatch to optimal power flow. Okay, this is where optimal power flow enters. So DC OPF formulation adds a linearized representation of the network, I mean, the network equation to the economic optimization problem. In DC approximation, active power flow of an transmission line is related approximately linearly to the difference in voltage angles between the connected buses. Okay, so line thermal limits can then be expressed as a linear inequalities. So the major advantage is that the resulting optimization remains an LP, I mean linear program, when the objective and other constraints are also linearized. The important assumption behind the DC approximation should be remembered here. So the voltage magnitude are treated approximately fixed, reactive power is neglected, and nonlinear sinusoidal relationship of the full AC power flow equation is replaced by a linear relationship involving angle difference. See, these assumptions introduce approximation error, but they provide a very useful computational model. This is why DC OPF is important in large scale operational optimization and market clearing. It provides network awareness without carrying a full nonlinearity complexity of AC power flow. So the word DC can be misleading because the network is still an AC transmission network. DC OPF does not mean that physical grid has become DC. It means that AC power flow relationship have been approximated by a linear model with assumptions that make the optimization tractable. So other applications across power sectors are when you use linear programming, it is having application throughout power sector. The first is generation scheduling. Instead of optimizing one operating point, we can optimize generator outputs over multiple time periods while respecting limits such as ramp rates and reservoir constraints. So if startup costs and other discrete decisions are ignored, okay, so many parts of scheduling problem can be represented linearly. So the second is the transmission expansion screening. LP models can be used as first stage screening tool to identify promising candidate lines or transformers before detailed nonlinear planning studies. So the third is load shedding minimization during an emergency. If demand cannot all be served, an optimization model can determine which loads should be curtailed while minimizing a specific penalty or priority cost. So the fourth is fuel and emission allocation. If fuels or emission allowances are limited, LP can allocate those resources across generators in a cost effective manner. The fifth is interchange. Okay. The fifth is interchange or wheeling optimization. When neighboring region exchange power, optimization can determine economical schedules subject to transfer limits. So the sixth is reserve procurements. required spinning and non-spinning reserves can be allocated across available resources at minimum cost. The common structure is always the same: define the decision, define the objective, impose the physical and operational constraints, and solve the resulting optimization problem. So, the common thread across these uh, application is allocation under constraints. LP is particularly useful whenever we have limited resource, competing uses for those resources, and non-linear, linear economic operational objectives. This is exactly the structure that appears repeatedly in power system operations. So, if you want to have a case study, LP based market clearing in practice, uh, see, at a high level, a market clearing optimization, uh, a market clearing optimization problem receives generator bits or linearized cost curves. These forms a economic objective. Uh, Demand forecast provide the power balance requirements. Transmission line ratings becomes network constraints. The optimization engine then determines an economical feasible dispatch. The dual side of the optimization provides marginal information associated with constraints. So, in network constrained market formulation, this information contributes to local pricing. Well, so So the transmission line ratings becomes network constraints. The optimization engine then determines an economical feasible dispatch here. So the dual side of the optimization provides marginal information associated with constraints in network constrained market formulation. This information contributes to locational pricing. The important idea is that optimization is not merely producing a list of generator outputs, it is simultaneously balancing economic objectives, demands, network limits, and other operating requirements. So in India, market and system operation processes involves institutions such as Grid India and the regional and the national load dispatch structures. So, the exact market design, clearing interval, bidding rules, and pricing mechanisms. These depends. Just give me a second. Yeah. So, the exact market design, clearing interval, bidding rules, and pricing mechanism depend on the particular market and operational process. So we would distinguish the general optimization principle from any one implementations. So the central work, uh, the central workflow remains, right. Generator bids or linearized costs become the objectives, demand becomes the balance requirements, network limits becomes constraints, optimization solvers produces the feasible economic dispatch. Uh, the optimization solver produces the feasible economic dispatch. The dual information can provide marginal values associated with constraints. This is a practical significance of mathematics we have studied today. So, it is useful to separate the optimization principle from specific market technology. Different electricity market use different formulation and settlement rules. What remains universal is the idea of an optimization problem, because optimization problem, balancing supply, demand, network constraints, and economic objectives. So, where linear programming reaches its limits? See, it is equally important to understand where the linear programming stops being adequate. The first limitation is approximation error. When we replace a quadratic cost curve with straight line segments, the linearized model is not identical to the original non-linear model. Increasing the number of segments can reduce the approximation error, but it also increases the size of the optimization problem. The second limitation is discrete decision. Generator commitment uh, a generator commitment decision is naturally binary. The unit is either on or off. A continuous linear programming variable cannot represent that decision correctly. Unit commitment therefore leads to mixed integer optimization. The third limitation is full AC network model. That is, AC power flow equations contains nonlinear relationships involving voltage magnitudes, voltage angles, active powers, reactive powers, network parameters. DCOPF deliberately simplifies these relationships to retain the linear structures. So, LP is powerful, but it is not universal. This is naturally, this naturally motivates for our third session, maybe day after tomorrow. Nonlinear programming allows us to retain the true quadratic cost curve and nonlinear AC equation at the cost of greater computational complexity and different mathematical properties. So the concept we learned today, we will not be discarded. uh, Standard formulation, constraint interpretation, corner point intuition, and duality remains useful foundations for the nonlinear optimization topics that will follow. So the limitation does not make DCOPF useless. It tells us when the approximation should be treated cautiously. If voltage magnitude, reactive power, voltage stability are strongly nonlinear networks, nonlinear effects becomes central to the problem. Okay, a full AC formulation may be required. So to completely look back of part 4, what we try to understand, first, true generator cost curve is often quadratic. Second, we approximate the curve using precise linear segment. Third, each segment becomes a decision variable with a constant cost coefficient. Fourth, we impose the power balance equation and segment capacity limits. That gives us a linearized economic dispatch LP. Then we add network constraints using linearized DC representations of power flow. That gives us DC OPF. The optimization now consider both economic and network deliverability. Finally, dual information provides marginal values associated with constraints. In electricity market formulation, these marginal values are related to locational prices, but there is a boundary. LP cannot directly represent true discrete commitment decisions and cannot capture full AC network physics without approximations. So, overall bridge is quadratic cost to piecewise linear cost to LP economic dispatch to network constraint DC OPFCs and finally towards nonlinear mixed integer formulations when the approximations are no longer sufficient. See, the final takeaway of the session 2, complete session 2. So, linear programming is a special case optimization, right, in which the objective and constraints are linear. The model relies on proportionality, additivity, divisibility, and certainty. Every LP can be formulated using decision variable and objective and constraints. Less than or equal to constraints can be converted using slack variables while greater than or equal to constraints use surplus variables and may require artificial variables for simplex initialization. For two variables, the graphical method allows us to visualize the feasible region. If an optimum exists, at least one optimum occurs at corner point. Simplex removes the two variable limitation. It moves algebraically from one basic feasible solution to another, selecting an entire variable from the objective row and leaving a variable using a minimum ratio test. Duality gives us another view of sample of same problem. Instead of asking only how to allocate resource, we can ask what those resources are worth at the margin. Finally, in power system, linear program becomes useful through approximation. Quadratic generators cost can be represented using piecewise linear segments. The resulting linearized economic dispatch problem can then be extended to network aware DCOPF. So the entire lecture is on one chain of ideas rather than a collection of formulas here. A useful final mental picture is this: the feasible region represents everything the system is physically allowed to do. So the objective function represents what we prefer economically, and optimization finds the best point inside the physically allowable region. So linear programming is powerful because both the preference, surface and restrictions have simple linear structures. Quick references, I mean references in the sense, this slide will give you all the formulas we discussed upon, and this will be very helpful. I'll share the PPT today. Anyways, we are ending up with this session 2. Okay, so this is much more quick reference formula sheet. Okay, the standard LP objective is linear combination of decision variables that you have it in maximum or minimum. Maximum or minimize the summation of Cj and Xj, right? Subject to you have lesser than or equal to or greater than or equal to. This thing we have discussed. For less than or equal to constraints, we add non-negative slack variables, some variables, right? Some of here you have Aijx plus Si equals Bi. Okay. For greater than or equal to constraint, we subtract a non-negative surplus variable, that is summation of this thing greater than Bi. Same formula, but it becomes greater than here. The fundamental theorem tells us that if an optimum exists, at least one optimum occurs at a corner point. In the simplex convention used in this discussion, the most negative coefficient in the Z row identifies the entering variable. The minimum non-negative ratio of right hand side of the positive pivot column coefficients identifies the leaving variables there. We stop when there are no negative entries remaining in the Z row. For the linearized economic dispatch problem, the objective is sum of the segment cost rates multiplied by segment outputs, and the sum of all segment outputs must equal demand. If you are preparing for an examination, I mean, these formulas should be very familiar. But more importantly, memorizing them is understanding what every term represents physically. See, do not try to memorize the formulas without the meaning. If you remember only the formulas for the ratio test but do not remember why it is required, you are likely to make mistakes when you solve those problems, because the ratio test exists because next basic feasible solution must remain feasible, right? So I have given you a set of practice problems here, 4 practice problems. So in question 1, it asks you to formulate a furniture production problem. The important part is not the arithmetic. Identify chairs and tables as the decision variables. Write the profit objectives and translate carpentry. I don't know whether you're going to solve it or not. So Again, you have 8 problems here. Then the last slide is about what are we going to learn in the section 3. Before we leave today, I want you to think about complete journey we made today. We started with a general optimization model from session 1. We restricted the mathematics to linear functions and obtained uh, sorry, yeah, yeah, obtain linear programming. We learned how to formulate an LP. We solved two variable problem graphically and saw the optimum occurs at a corner point. We then used the simplex method to reach the same optimum algebraically. We introduced slack, surplus, artificial variables, and duality. Finally, we applied the ideas to power systems through piecewise linear generator costs, linearized economics, dispatch, DC optimal power flow. If you remember only one conceptual chain from this class, remembers this. A real engineering problem is first translated into mathematical model, right? The quality of the optimization result depends on the quality of the model. LP provides a particularly powerful framework when the objective and constraints can be represented linearly. In a power system, linearization allows us to trade a controlled amount of modeling accuracy for conceptual speed and scalability, right? That is the real reason linear programming matters in power system optimization. So we will continue in session 3 with non-linear programming, dynamic programming, load flow, and introduce to full optimal power flows. See, optimization gives a recommended operating point under assumptions and constraints includes in the model. It does not automatically guarantee that every real world condition has been captured there. Okay, so engineering the judgment, engineering measurement, protection, uh, operational procedures, and system security requirements are very much essential. You have to understand this. Fine. So this brings to the end of our section 2. I mean session 2.